Okay, so domain and range of combined functions. Now for a start one, we'd hope you'd be able to combine them. In this case, fx is the inside one, gx is the outside one, so I have stuck fx into gx. At this point, the easiest way to solve is to multiply that by x minus 1, and that by x minus 1, and that by x minus 1. So if you're going to simplify this properly, we've got 4x minus 4 at the top here. At the bottom here, we've got 2 plus 3x minus 3. And so overall our graph is 4x minus 4. And over, let me just erase this, over 3x minus 1. Okay, so when you're combining the graphs, you don't really have to focus too much on this thing here in terms of the domain and range. What you do have to focus on is the domain and range of fx and gx by themselves. So I'm going to put the domain of fx here and its range there, and the domain of gx here and its range there. So fx is the inside function, and you can start off just by noting its domain and range. So this is 2 over x minus 1. So we know that the domain x cannot be equal to 1. So we know that x is not equal to 1. Otherwise it's undefined. Furthermore, if you think about what this graph looks like, this is a hyperbola. It's a hyperbola that's gone across one unit to the right, which is of course why x can't equal to 1. And it looks like this. So from this graph, there's another asymptote, and that is the y. So y also on this graph cannot equal 0. So I'm just going to put a 0 there. So x can't equal to 1, and the y of this graph can't equal to 0. Then for gx, we have the y cannot equal to 0, because again it's a hyperbola, and so you can imagine if you saw this one's gone 3 to the left, so it's sitting there like that, it's sitting there like that, it's sitting there like that. For absolute certain, the y value cannot equal 0 because there's an asymptote there, and at the same time the x value cannot equal to negative 3. So it's not equal to negative 3, and this one is not equal to 0. So now you have to work out, to get your combined domain and range, what you have to work out is what was allowed to go in and what can possibly come out, right? So what goes in is whatever's in here, and that's your domain. And whatever comes out here is your range, right? So first of all, this one over here has an effect on what can come out of this. So this is your range of your fx function is now the domain of your gx function. So we're saying that the x value of gx cannot equal to 0. So if x is equal to 0 for gx, then we'll have 4 over x plus 0 plus 3. And gx will equal to 4 over 3. So this one means it cannot equal to 4 over 3. The y value cannot equal to 4 over 3. And that is for gx, right? That is when it comes out. And that is because the x values that go into fx have an effect on the range of fx, and the range of fx is the domain of gx. And so obviously it's going to have an effect on the range of gx. Then going the other way around, the domain of gx has an effect on what can be put in, because you can't get a minus 3 out, right? So if I make, if I cannot have 2 over x minus 1 is equal to minus 3, because if it is, then the domain of the combined function won't work, right? So you have to have 2 over x minus 1 not being equal to minus 3. So if I multiply that out, I get that x is not allowed to equal to 1/3. So x is not allowed to equal to 1/3. And that is our final domain and range. So the domain for this one, the final combined domain, is that x is an element of real numbers, but x is not allowed to equal to 1, or a third, right? If x equals to 1, then, well, that's impossible for fx, because then the function doesn't exist. Then fx doesn't exist, in which case you obviously can't put it in gx, right? If x is equal to 1/3, then it means that when we place the 1/3 in here, we are going to get 0, and then gx is undefined. So that doesn't work, right? And then for the range of the original function was that it can't be equal to 0, because if it is, you can imagine if you were to solve this one for x, you'd end up with something over gx, and then it would also be undefined. It's also obvious from the asymptote. So this second function, the range cannot be equal to 0. And in addition, because the range of the first function can't be equal to 0, the range can't be equal to 4/3 either, because it's impossible you can't put that 0 in, which means you can't get 4/3 out. So the range is y is an element of real numbers, and y is not allowed to equal to, I should do this properly, so let me write it as g of x. Don't know where my voice is going. G of x is not allowed to equal to 0 or 4/3. So in these two circles, we put the domain and the range of the first one. And in these two circles, that is given, right? In these two circles, we'll put the domain and the range of the second one as they're given, right? Then we'll have a look at how the domain of this one affects the domain of the original one. And we'll have a look at how the range of this one affects the range of the final one, right? So that's the aim. So the domain of the first one, it's a little surd graph. You should know what square root of x looks like. Looks like that. So its domain is x is greater than or equal to 0, and its range is y is greater than or equal to 0. The second one is is 2x minus 7, just linear. There are no restrictions on it. So you can basically keep both of these two circles blank, right? This one, we'll just make it blank, keep that one blank, right? Because it has no restrictions, okay? However, there is certainly possible that this fact that y can only be greater than or equal to 0 has an effect on this combined function. So this y value here happens to be the x value inside that inside gx, right? So that value has to be positive. So if you've got, or 0. So if it's positive or 0, then the smallest number the range can possibly be is minus 7, right? So if we have g with 0, then we're going to have 2 times 0 minus 7, and that's the smallest possible number we have. Otherwise, the value has got to be bigger than 0. So we can have 2 times 1 minus 7, which is minus 5, right? But we can't have anything smaller because it says that the basically, and it's probably better not to put the y in because it gets confusing. But basically, this value over here has got to be greater than 0. That's the value that's going to be there. And because it's positive, then the smallest possible value that this one can have is 7. So it must be greater than or equal to negative 7, right? So our combined domain is x is greater than or equal to 0. X is an element of real numbers. And the range is y is greater than, or again, it's not nice to write it like that. Don't write it like that. So write it as g f x is greater than or equal to negative 7. And it's also an element of real numbers. So I guess I'll just squash that in the bottom. Okay, so that is combined domain and range. I think I'll probably put in one more example. Okay, here's another one. So again, we're going to put fx inside gx, which I have done there. So I've combined them. That's the easy part. Now we're going to first look at the domain and range of fx, then the domain and range of gx, and then we'll see how the range of fx, so the range of fx becomes the domain of gx. So it's going to affect the range of gx. And of course, the domain of gx determines what's possible to be the domain of fx. Okay. So starting over in the beginning, if we look at 9 minus x squared, if we look at the square root of that, no one would expect you to know this graph. But you do know that the square root of anything has to be positive. So 9 minus x squared is going to be greater than or equal to 0. We know that as a fact. If you solve that and you factorize it, so we've got 3 minus x and 3 plus x, and you solve this using the number line as you're supposed to, you're going to get shown that range over there. So this means our x value has got to be between 3 and negative 3. Otherwise, this very first function ceases to exist, in which case you obviously can't combine them. Okay? And then the range of this first function, as you can see, the highest it goes up to is 3 from the graph. But again, no one would expect you to see the graph, but one would expect you to understand that if I put in any value of x under here, it's going to make it smaller than 9. So the smallest thing x can be is it can be, and we've got negative 3 and negative 2. If we have negative 2 squared, for example, it'll become something positive because you're squaring it. So you're squaring your x value, and as a result, it can reduce it. So the smallest, if x is equal to 0, that's the absolute smallest, it's the value that will create the smallest y value. So y is therefore clearly between 3 and 0, and you don't need the graph for that. If y is between 3 and 0, then if you look at these values over here, so that this is now going to be the range for, well, this is now going to be the x value for this. So in other words, these values over there are going to be in here, okay? So 2 times 0 plus 3 is 3. So if it's 0, then the biggest value, if this value here is 0, then gx is going to be equal to 3. If this value here is 3, then gx is going to be equal to 6. So it's going to be 2 times 3 plus 3, which is in actual fact 9. Okay? So then the only values that y can be is they can be between 9 and 3. So we've got the outcome for y. The x values going into it have got to be, the smallest possible one is 0, and the biggest possible one that can go in is 3. So 2 times 3 is 6, plus 3 is 9. In actual fact, this one has, because it's a linear expression, it's got no limitations on its range, so it's not going to have any effect on anything going backwards, and it has no limitations on its domain. So what you see is the final outcome. So the combined, go away. The combined domain is x is smaller than or equal to 3 and greater than or equal to negative 3, and x is an element of real numbers. And the combined range is going to be gfx is an element of starting at 3 and ending at 9. It's a nicer way than writing the set builder notation. I hope that's helpful. We can practice some more. But basically what you're going to do is your first steps are to record in this first circle your domain of f as it is decided by its original equation. Then you're going to look at what that means for its range according to its original equation. Then you can forget everything else and just go and look at the final equation, gx by itself. Don't worry about the blended one, just look at gx and work out what is its range and what is its domain, right? Once you've done that, then you look at the effect of the range of fx on the domain of g, and you look at the effect of the domain of gx on the domain of fx. And that's it. And that works very well.